Assalamualaikum warahmatullahi ta'ala wabarakatuh. Okay, so we'll start the class with the Ummul Kitab Al-Fatiha.
Waalaikumsalam, sir.
Okay, for for our last sessions of PHY 098 lecture today, so I will give or I will explain back, okay, the subtopic for the nuclear physics and also the nuclear reactions that we learned yesterday, and that you already saw this video with a pre-recorded video yesterday. So today I will explain back. So I'll try to share the slide first. Okay, can you see the slide?
Yes, sir. Yes, sir.
Okay, very well, very well.
Okay, so here
Right, so this should be the topic, the nuclear physics and the nuclear reactions. Okay, so these are the subchapter of from the nuclear physics and the nuclear reactions, which is the constituent and the structure of nuclei, and also the radioactivities and the decay process. So we have two subtopics for chapter 29. All right, so at the end of this lesson, the student should be able to, if you look carefully, this one contain a lot of definitions. Okay, define, right? Define atomic number, a neutron number, mass number, for example. Define isotopes. Define, okay, the mass unit. Define the size of nuclei, for example. Okay, and also we have to explain the alpha decay. Okay, alpha decay, a beta decay, and also a gamma decay. Okay, and we have to also to calculate the energy release. Okay, whenever there's something happens to the electron or something's happened to the nucleus, for example, so they actually can release the energy. Okay, from the alpha, beta, or gamma decay, all of them will create energy. Okay, we release some energy, so we need to calculate that, and also we need to define the half-life or using the radioactive nucleus. Okay, so this is the constituent and the structure of nuclei for the subtopic of the nuclear radiations. So in this, we learn about nucleus that contain positively charged, okay, positively charged protons and a neutral charged neutron. Okay, so inside the nucleus itself have proton and neutron. Okay, the nucleus are characterized by the number of proton and neutrons then they contain. Okay, with the formula of A, which means the mass number, equivalent to atomic number Z, and also N, the neutron number. So atomic number represent proton, while the neutron number represent neutron. So inside the nucleus we can have a proton and also neutron. Okay. So the notation for a particular nucleus of element X is written as X equivalent to A, okay, and also Z. Okay, we don't put N here. We don't put the neutron number. In fact, we just use mass number and also atomic number. Remember, atomic number is also the significant value for proton. Okay, so we can measure, we can calculate the number of proton using atomic number. For example, we have carbon 14 over here. Okay, carbon 14. Okay, so right now, okay, we know exactly that the number of proton in the carbon 14 is 6 because this is the atomic number, while the neutron number should be 14. Okay, minus 6, you get 8. So this should be the neutron number for carbon. However, for the aluminium 27, okay, aluminium 27 and also 13. So 13 should be the proton number. Okay, so proton is 13, while neutron will be based on 27 minus 13. So you will get 14. Okay, the number of neutron is 14. Okay, slightly greater than proton inside aluminium. Okay, so the masses and charge of atomic particle will be based on the kilogram. Okay, will be based on mega electron volt over c square, and based on U, and also there are 3 types of mass that we are talking now. Okay, so normally we only talk about kg, which means the mass, gsin, right? So for the proton, you'll have 10 power of negative 27. Same goes like neutron, but just a little bit different in terms of decimal point. But in the first 2 decimal point, okay, all masses in kilogram are the same for proton and neutron. But in fact, for the electron, okay, the number of the mass of electron is much more lower compared to proton and neutron with the 10 power of negative 31. Okay, so proton, neutron, and electron is also can be written up using mega electron volt over c square. Okay, mega electron volt over c square. So we can also give mass because this one is using E equals to mc square. Okay, E equals to mc square, where m is what? M is E over c square. And how about E? E is the value of energy over speed of light. So energy, this is the value, mega electron volt. Why? C square is c square. So that's why the unit for mass can be written as mega electron volt over c square. Okay, and the number 3 is the mass can be, you can also write down the mass using AMU. Okay, AMU, atomic mass unit, or we can short form this one into U. Right, so the value of proton is like 0.07276. Okay, the decimal we have a lot, I think 6 decimal point, and the neutron is a little bit different. Okay, we have increased in the atomic mass unit 8665, while the electron is much more lower compared to mass of atomic mass unit of proton and neutron. Now, how about the charge that you already know? For the positive and negative charge, they're all the same. It's like just the number of just a sign of positive and negative. While for the neutron, the charge will be 0. Okay, so the atomic mass unit U is defined that the mass is exactly 12 U. Okay, for example, we have 12 C. Okay, this is carbon 12. Okay, carbon 12, you can refer to the periodic table. Okay, the carbon have 12 mass number. Okay, while the carbon have 6 for the atomic mass. Okay, atomic number is 6, while for the mass number is 12. So you can write down this carbon in terms of AMU, in terms of atomic mass unit, with the just refer to the mass number. So we can write down as 12U. Okay, while U itself, okay, U itself is the have conversions, okay, which is 1U is equivalent to 931.5 mega electron volts, excuse me, over c square. Okay, 1U is equivalent to 931.5 mega electron volt over c square. Okay, so normally when you calculate the, let's say in the future, when you calculate the binding energy, the fusion or the fission, you need to use atomic mass unit. Okay, and will use a lot of E equals to mc squared. Okay, afterward I'll show you. Okay, the careful measurement have related the size of the nucleus to its atomic number here. Okay, 1.2 10 power of negative 15. That equivalent to m times e square root of 3. Okay. By contrast, the radius of an atom is an order of 10 power of negative 10. This means that the density of the nucleus is extremely high. Okay, so the properties. Okay, the properties of the nucleus. Okay, the properties of the nucleus. The strong force is short range, acting only the distance of a couple Fermis. Okay, Fermi means 10 power of negative 15. Okay, this is Fermi. Okay, the strong force is attractive and acts with a nearly equal strength between proton and neutron, and neutron and neutron. Okay, so this is a few examples that not really generate the values. Okay. Okay, so now we move to the radioactivity. Okay, the radioactivity is what? Okay, so this is due to the nucleus. Again, now we talk about nucleus. We'll talk about nucleus, but the unstable nucleus. What type of nucleus? The unstable one. Okay, if you can refer to the periodic table, we can see that a lot of elements have been lined up, arranged, so that it will be based on the group. Okay, a group of maybe an electron valence whatsoever. Yeah, you learn this thing in chemistry. Okay, and we can see that at the end of the periodic table, okay, some of the elements are unstable. How can we know it is unstable? Because it's stated there in the periodic table that the nucleus is unstable due to what? Okay, so due to the conditions of the nucleus or conditions of the element itself. Therefore, in order to make it stable, okay, the nucleus that is unstable, okay, can either, okay, what? Decay. Okay, so the stable, in order to be stabilized, okay, the nucleus can either decay, okay, or what? Returns to the ground state. Okay, return to the ground state, meaning that the nucleus that is unstable always excited. Okay, excited. Try to jump around here and there in order to emit or to radiate the energy. Okay, so so that will cause the unstable of the nucleus. Okay, if you can remember, the electron will jump up and down using the orbit from orbital one. If you notice, using the Rydberg equations. Okay, 1 over n square minus 1 over m square. Okay, so you can see that a lot of elements or a lot of electron is on the edge of what you call it as an orbiting, and if the electron move around, okay, if electron jump around, okay, jump into a more higher orbiting, so it will cause the nucleus to be unstable. So in order to do that, the nucleus should either be decay, okay, kurang balik, decay, or return to its original or a ground, should we call that as ground state. Okay, so the various emission that results are known as radioactivities. So in the radioactivity, when we talk about radioactivity, we should know. So you have alpha, beta, and lastly gamma. Alpha, beta, and gamma. Those are the various emission that results in the radioactivity. Okay, so how about alpha, beta, and gamma rays? Okay, well, whenever we talk about alpha, we can put particles after alpha. So to be the beta. Beta. Okay, alpha is particles. Beta, maybe we use a beta ray. Some books use a beta particle. Okay, but this book, survey books, or maybe a Pearson books, use a beta rays. So that's with the gamma. Gamma also use a gamma ray. So the outcome, Okay, the outcome of the radioactivities will give alpha particle, beta rays, or gamma rays. So these are the penetrating abilities for the alpha, beta, and gamma. You can see the power of we compare between these three rays. Okay, you can see that the gamma is very powerful in terms of how they can penetrate the materials. Okay, because the gamma rays can penetrate several centimeters of lead. Okay, so for beta rays, yeah, maybe electron or positron. Okay, electron is here. This is electron. Beta negative, that means electron. Electron means you have a more negative charge compared to positive charge. But beta positive is considered to be positron or electron with the positive charge. Okay, don't be confused, don't get confused. It's just an explanation in how can we relate electron and positron only on this topic. Okay, can penetrate a few millimeters of aluminium. Okay, can penetrate a few millimeters of aluminium. Definitely not. The beta rays cannot penetrate lead. Okay, but aluminium, okay, can only can penetrate aluminium. Beta rays can penetrate aluminium, but not the lead. Okay. However, if you look at the alpha particles can only can barely penetrate a sheets of paper. Okay, so when you see the paper, so maybe alpha rays cannot go through that paper because it can barely penetrate. So it's very hard to see alpha rays penetrating a paper. So don't try to find where is alpha ray whenever you have aluminium or lead. Okay, so this is the alpha decay. So in alpha decay, a nucleus decays by, okay, this is the conditions, emitting alpha particle. It loses 2 protons and 2 neutrons. 2 protons and 2 neutrons. Remember, okay, whenever neutron plus proton, so it will give you mass number. It will affect the mass number. Remember, the element is X, okay? Okay, the element is X, while you have A, the mass number, and Z, the atomic number, or also known as proton number, and X is the what we call as parent nucleus. Okay, X is parent. Okay, while Y here is the daughter nucleus. Okay, daughter nucleus. Okay, so obviously parent. Okay, and daughter nucleus. What happened to the daughter nucleus whenever it emitting an alpha particle? So because of the it loses 2 protons and 2 neutrons. So the mass number will be affected by minus with negative 4, or the mass number will be minus 4, and the atomic number will be minus 2. And this value, okay, is associates also with the helium, another atom of helium-42. Okay, so for example, we have uranium-238. Okay, you have uranium-238. So the number of proton is 92. So when you want to calculate the number of neutron is 238 minus 92. So you will get 146 here. So this is the proton and neutron. So whenever, as I said earlier, that nucleus, if the nucleus wants to be okay, the nucleus wants to stable, so it needs to do decay. It's either using decay or radioactivity. So the decay of the uranium-238 now will be based on the emitting of an alpha particle. So you know, when you see alpha particle, the words of alpha particles, so definitely you need to remember, now you must have helium-42 in the equation. So in order to balance between the equations on the left and equations on the right, so you need to measure it. Okay, so the daughter nucleus, we doesn't know yet the value of the A. So let's say A is 238. 238 minus 4, you will get 234. 4. While for Z, Z is 92 minus with 2. So you will get 90. So now using the periodic table, you can find what is the mass number 234 with the atomic number of 90. So the answer should be TH or thallium. Thallium. So in the end, after the decay process, it will leave with the thallium as a daughter nucleus, and it will also release some helium. Okay, helium-42. So helium-42 is called emitting and alpha particles. Okay, this is the examples of the daughter nucleus. This is example of how you can measure. Let's say part A to calculate the daughter nucleus, and B the energy release. Okay, so regardless of how tough or how complicated this topic can be, okay, the examples or the questions that will be based on these topics is quite 100%, 100%, should I call that as easy? Okay, you need to carefully calculate those values, because why? Okay, let's look at this example. Okay, now we have the question, determine the daughter nucleus. Number one is to determine the daughter nucleus. Now, okay, what conditions undergoes alpha decay? Okay, when the questions include the alpha decay, so you know you need to think that this particular atom must be reduced or must be find using the decay of the alpha particles. So in the end, so now you have a parent nucleus, which is uranium 23892. So what is the daughter nucleus? So the daughter nucleus will be, let's say you put Y. Okay, 238 minus 4, while 92 minus 2. Okay, plus with helium 4, okay, helium 4, 2. All right, so the answer is Y is 234, and the atomic number will be 90. So the answer is TH thallium. So that will be the equations. Okay, that will be the outcome from the daughter nucleus, from the parent nucleus to daughter nucleus. Okay, the other parts of this topic is to calculate the energy release when uranium-238 undergoes alpha decay. So how to calculate that? Okay, in this case, okay, you have been given, or you have been asked to look those kind of value inside the appendix. Okay. This is your appendix, right? So if there are if the question doesn't give you appendix, so you need to ask. Okay, but that one is in terms of, let's say, when you say when you undergoes the face-to-face examination. But at your home, maybe you can refer to your books, to your survey textbook, or maybe other values, but will be based on the equations of the decay, alpha decay. Okay, so first of all, you need to find what is the, so this arrow represent what? Represent, this one is the input, or should I call it initial, and this one is the final part. So initially, you have uranium-23892. So for those who have a survey textbook, now you can return to the back of your book. Okay, not so back. Okay, there's a few pages from the top cover. Okay, so from back, backward, obviously. So you will have a parent nucleus and also a daughter nucleus. So you need to find what is the energy. So energy associated here will be based on the atomic mass unit. So remember, to find atomic mass unit for uranium. Remember, uranium is not just 238. Okay, maybe inside the, maybe if they want you to doesn't want you to find it everywhere, or to find it in the internet, they will provide you with the question. So inside the question, they will put uranium-238 berapa. Okay. Berapa. So dia akan mention. But if you can refer to the appendix, okay. So on the left side is the energy initial, and on the right side will be energy final. So you need to use the atomic mass unit. So given that the initial will be 238.050786, you need to take every values, every decimal points. Okay. So everything. So in the final, so final here we have 234. What is that? This is for this thing. And you have also 4.002603 will be the mass number of this alpha particle. So in the end, you will get a set of initial and final. So in order to do that, you need to use the delta M. Delta M will be based on M final minus M initial. So what is M final? Regardless of the value will be negative or positive, then you can use E equals to mc squared. Okay, very famous equation. E equals to mc squared, but to be exact, E is what? E is equivalent to delta's modulus M, modulus delta M c squared. That is the simplest one. Okay, so E equivalent to modulus of delta M over times with C squared. Okay, so the mass now will be based on the difference of the mass. So the difference of the mass, if they are negative, remember to put a positive value because it should contain the modulus. And in the end, you can find what is the energy released. That energy is equivalent to delta M C squared. That is the real term. Okay, not E equals to mc squared, but delta M. Okay, a modulus of delta M C squared. Okay, look at how they cancel out each other. So this is the value, you put it here. Okay, now you cancel out U. Now you cancel out C square. So in the end, you will get 931.5 mega electron volts times with 0.04587. The answer will be 4.273 mega electron volts. Okay. So that is the beta decay, alpha decay. Now we look at the beta decay. So what is the difference between beta and alpha? So a nucleus that decays via beta decays emits an electron and positron. So there are two outcomes from the beta decay. Okay, well, one outcome for the alpha decay because we only at the the things that goes out from the nucleus will be helium-42. So in this case, it will create or it will emits an electron. Okay, emits electron or positron. Okay, so if we have electron in the equation, so might be you need to plus with 1 because the electron is the what we call it as negative charge. Okay, so the electron when electron will be in the equations, so you need to add up some values. Okay, well, if we have positron, then the C will be -1. Okay, there is a third particle emitted which has no electric charge and little called the neutrino. Okay, so this is the symbol of the neutrino. Okay, so now we look at another example. So in this example also, but is using carbon-14. The number says carbon-14. Then you need to measure what is the daughter nucleus. So the daughter nucleus will be nitrogen-14, 7. Okay, so that's how you calculate. You find out what is the initial, what is the final one. So in the end, you will get to them. So delta M equivalent to MF minus MI. So you will get negative over here, but don't bother about it because it should contain the modulus. So the answer will be 0.156 mega electron volt. Okay, so this is another examples, but this one is using beta particles. Okay, emitting a beta ray or beta particle of sulfur, for example, sulfur 3516. Okay, so determine the energy release in each reaction. That will be the normal question. Energy release, energy release, energy release. Okay, so in the end, we should be what we call that, arrange the algebraic or arrange the elements. That's one. This is the value 3516. Okay, you will move to the parent, the daughter nucleus. Now it creates another uh, electron and also neutrino. Okay, but neutrino we doesn't use equations. So the Mi is what? Mi is 3516. So Mf will be everything that goes on this side. Okay, you need to find what is the atomic mass unit for the chlorine, chlorine 35. Okay, electron and also neutrino. Okay, so in the end, the process are still the same. Okay, now you can see the delta M clearly in terms of E equals to delta MC square until it will get until mega electron volts. Okay, so for the gamma decay is emitted when an excited nucleus returns to its original state. Okay, a gamma ray is emitted when an excited nucleus returns to its original state. Nuclei may become excited through alpha or beta decays. For example, you cannot have alpha decay over here. Okay, we can only put beta or gamma decay. So how come we know that that will be the gamma decay? So starting from 14,6, the carbon, so it excites to the next level of orbital, it becomes, okay, 14,7, nitrogen. Okay, and of course, how can I know? Yes, this, but just looking here. Okay, and electron negative cause electron times with the neutrino. Okay, so but the nitrogen 14 is not stable yet. Okay, so this should be the excite the nucleus. Okay, the nucleus will excite will compare to them because 14,7 neutron with the asterisk. Yeah, this is the asterisk. Cannot find from here. So this is quite special. The decay process will continue until stable nucleus is reached. So that particular stable nucleus now, okay, now being converted to no asterisk, and of course plus with the this symbol. Why is this symbol? This is gamma. Okay, gamma ray. Okay, so when you have a uranium-235 and also atomic number 92 decays, it passes through a number of intermediate nuclei before reaching the stable end of the series. For example, from uranium-235 92, now we must go to the plumber Pb, that equivalent to 20782. Okay, so how they did? Yes, they calculated mass number over atomic number, while you have a uranium at this side. This is uranium-235. This is beta decay. All right. So note that some intermediary nuclei can decay in only one way, whereas others have two decay possibilities. Okay, this should be the activities. All right. The 2 units of activity is either using Curie. Okay, that equivalent to what here? 3.7 10 power of 10 decays per second. Okay, and also we can define the activities of the nucleus using Becquerel. Okay, 1 Becquerel is equivalent to 1 decay per second. Before this is equivalent to 3.7 10 power of 10 decays over second, while for the BQ, which means Becquerel, is equivalent to 1 decay over second. Okay, now we move to the half-life and radioactive dating. Right. So what is half-life? Okay, it has been discovered that the radioactive decay can be used to date a numerous item. Okay, so this is the function of half-life. Okay, that particular radioactive can decay and can be used to date numerous items of interest from the recent and in the past. When nuclear decay acid in a random process on average of a given fractions of the original number of nuclei, thus the number of nuclei and remaining at time. Is it T is given by this expression n equals to n naught at half-life T. Okay, while the half-life is called decay constant. Okay, it's not a angular frequency anymore. It is a decay constant. Okay, and T is time and N is the original numbers, right? Okay, so you can see here now we have plotted the graph of N versus N naught and also time T equals to T in second units. Okay, units of second. Now you look here at 4 second -1 and also 2 second -1. Okay, which means all of this value is considered to be half-life. Okay, so you can measure the value using the graphs. So what does it say? The larger the decay constant, remember, the larger the decay constant in lambda, the more rapidly the populations of group of nuclei decreases. Okay, the value of lambda doubles as we move downward from one curve to another. So which is here. Okay, so this is the good practice. We have iron 59 is used in the medicine to diagnose blood circulation disorder. The half-life of iron, so half-life, kita tanda sikit buat macam tu, ialah 1.55. Okay. Decay constant, sorry, that is not 55.9. Iron is 59. Okay, so the half-life will be 44.5 days. Okay, so the question now is how much of 2000 milligram sample will remain after 133.5. So we need to calculate the using n minus n naught. But to simplify these things, now we have lambda equals to 44.4. Okay, so now we need to differentiate. We need to ratio that the 44.9 days when compared to 133.5 days. So we need to calculate this first. 133.5 divided by 44.5. Okay, so when this happens, we can calculate this one is equivalent to 2. Okay, 3 half-life. Okay, 3 half-life. So now, okay, with the 2000 gram, 000 milligram, what is half-life? If from 2, it becomes 1. Okay, 2.000 and 1.000. Because it's half than 2, so 2 bagi 2 dapat 1. Okay, and 1 digerak lagi dapat berapa? Divide, they can get 0.5, and 0.5 digerak lagi jadi 0.25 milligram. Okay, milligram. So what is the number? This is 1, this is 2, and this is 3. Okay, 1, 2, 3. So meaning that there are 3 half-life. Okay, this is how they used to date the living organism or the Earth's atmosphere using the carbon-14. The carbon-14 is the isotope for carbon-12. So the activities, when the organism dies, the carbon-14 activity decays exponentially with half-life of 5730 years. Quite long. Okay, it's not just like after before this.
Okay, so
Okay, so you have any questions? Ada soalan tak? For the things? Do you have any questions?
So untuk beta decay,
Okay.
dia keluarkan dua partikel.
Macam mana?
Dia keluarkan dua
Tak, dia
partikel.
keluar salah satu. Dia keluarkan salah satu je. Either elektron ataupun positron. Elektron or positron. Simple. Kalau elektron maksudnya kita kena plus 1 dia punya Z. Kalau positron maksudnya kita kena minus 1 dia punya Z. A dia maintain sama. Okay.
Macam mana nak tahu kalau dia nak elektron atau positron?
Okay, dia depends kepada biasanya dia akan bagi gambar ataupun dia akan mention dalam soalan. This use beta particle. Kalau dia just use beta particle maksudnya elektron je lah. Dia buat elektron lah. Okay. Kita risau kalau dia mention beta particles tapi dia cakap positron. Okay. Kalau positron kita understood. Ada soalan lain? Okay. So kita teruskan dengan last topics. Okay, last topic ni saya akan play juga, tapi saya akan play mengikut slide mengikut slide PowerPoint. Okay, kalau after diterangkan oleh madam tu saya akan terangkan pula. Okay, saya akan buat terus. Now we look.
Assalamualaikum and good day everyone. So today we are going to continue with chapter 29 where we have 29.2.
Can you hear the voice? Boleh dengar suara ke? Boleh dengar ke? Tadi? Sekarang ni memang tak ada. Tadi. Dengar tak suara?
Tak kuat.
Tak kuat sangat sir.
Yeah. Okay, I need everybody to use your your earphone. Cuba pakai earphone. For those yang tak pakai, tolong pakai sekarang. Kalau tak dengar juga, I have to play the pre-recorded video lah. Okay, please. Cuba dulu
At the end of this lesson, you should be able to define and calculate the binding energy, apply nuclear reactions, and describe the application of radiation in medical. 29.2 binding energy. The mass binding energy. The mass of any stable nucleus is less than the sum of the masses of the protons and neutrons it contains. This difference in energy, which is multiplied by c squared, is called the binding energy of the nucleus. Okay, so the mass of any stable nucleus. So what is this? So let's take a look at this hydrogen 1. So the mass of this hydrogen 1 is always less than the mass of the proton and neutron it contains. So for example, in this hydrogen 1, it has 1 proton and 1 neutron. So we need to calculate the mass of the proton and neutron and compare it with the mass of the nucleus, which is hydrogen 1, and the difference between these two is the delta M. So this difference in energy multiplied by C squared, right? The difference in energy multiplied by C squared is called the binding energy, and the unit is in mega electron.
Okay, I will explain a little bit of this. Okay, so what does it means by the difference in this? So now we need to use E, okay, equivalent to delta M C squared. Okay, so what is the difference in energy? Difference in energy means that, okay, these things. Okay, while C here untuk untuk this chapter, untuk this topic C, kita tak tukar dia. Okay, we don't define C as 3 times 10 power of 8. Kita tak buat macam ni. Why? Because dekat C tu kita dah the C itself. Okay, C ni apa dia? C square ni adalah apa dia? C square ni adalah mega electron volt over C square. Itu ialah C square. Dalam buku survey dia akan mention that C square is equivalent to mega electron volt over C square. So bayangkan kalau kita replacekan C square tu dengan mega electron volt over C square. Okay, so in that case dia akan cancel out C square yang ini dengan C square yang ini. So therefore kita tinggal dia mega electron volts. Okay, so sama juga macam tadi. So the binding energy now is the difference in the mass itself. Okay, energy in terms of mass. Kenapa dia kata macam tu? Contoh dia. Okay, saya ambil satu contoh, hydrogen. Okay, hydrogen, we have hydrogen 2,1, for example 2,1. So the proton is 1, while the neutron is also 1. Okay, 1 plus 1, so Z dia, A dia must be equivalent to 2. So that's why kita boleh arrange dia macam ni. Okay, so let's say, so the mass of proton and the mass of neutron, okay, tak apa, kita dengar dulu Madam dia cakap apa. Tengok dulu.
As what I mentioned, the binding energy is given by the equation of delta M times squared. Binding energy is defined as the energy required to separate the protons and neutrons from nucleus. Delta M is the change in mass, right? Between the mass of the proton it contains and the mass of the proton and neutron it contains with the mass of the nucleus itself, right? So when we multiply this delta M with C squared, which is given by 931.5 mega electron volt per 1 U, we will get the binding energy, where the unit will be in mega electron volt. You can refer to Appendix B in your textbook for you to be able to calculate the binding energy of any nucleus. So for example, let's say you want to calculate the binding energy of lithium, right? Lithium-63, for example. So how do you want to calculate that? So first, what do you need to do is say lithium-63. So how many proton? You have 3 proton and 3 neutron, right? So we need to find the mass of the proton and the mass of the neutron it contains, right? So we have 3 proton plus 3 neutron. Find the mass, right? So the mass of the proton, 1 proton is equivalent to this, which is 1.007825. Why is it the same with the hydrogen 1,1? Because hydrogen 1,1 only consists of 1 proton and 0 neutron. So basically, the mass of hydrogen 1,1 is actually equivalent to the mass of 1 proton. So we take this value of 1.007825 as the mass of the proton, right? Meanwhile, for the mass of the neutron, right? So it's given in the table, which is mass of the neutron is 1.008665. So So we calculate the total mass of the proton and the total mass of the neutron, right? So we get this, and then we compare it with the mass of the lithium-63 itself, right? So we have, where do we get it from our table? So we can see here lithium-63. So this is the value, right? Which is 6.015122, right? So you find the delta M, the difference between those masses, the total mass of this proton and neutron with the mass of the lithium, for example, and then you get this multiplied with the C squared, right? So you will get the binding energy of lithium-63.
Okay. So these are the appendix that I said just now about how can you refer the appendix of the atomic mass unit. So this should be the atomic mass unit here. This is all atomic mass unit. If you can refer, this is quite the elements. Okay, lots of elements from atomic number Z equals to 0, okay, which is the neutron, until the plutonium. Okay, and if you carefully see, just look at the carbon part. Okay, you can see that carbon have a mass, a different mass number. Okay, maybe carbon 10, okay, carbon 11, carbon 12, carbon 13, carbon 14. So a lot of atomic mass numbers. So you need to establish those kind of value. Okay, so that will be the when you see the different isotopes will give you different atomic mass unit. Okay, so in this case, you need to calculate the binding energy. What is binding energy? The energy that wants to separate the proton and the neutron from the nucleus. I can define that. If you have nucleus, so let's say this is nucleus. So inside here we have proton and we have neutron. So there are some energy that hold this proton and neutron. Okay, so if you want to calculate it, so you need to get rid of this proton and neutrons energy from the, so the nucleus have energy. So you have energy of the nucleus and also the energy of proton, and so we need to find the difference in mass of these two things. Okay, so you need to calculate how many proton, how many electron. For example, okay, we need to calculate the lithium-63. Okay, so the lithium-63. Okay, so by our calculation, the lithium-63, the proton will be 3, while the neutron is also 3. Okay, so by comparing of the mass, so 3 times P untuk proton and N untuk neutron. So you need to compare it. So 3 times how much P. Okay, so proton untuk lithium, so 6.0 something else. That is the nucleus. Okay, itu ialah untuk nucleus. Tapi kalau untuk proton, berapa value dia? 1.007825 plus with 3 kali dengan 3 neutron. Neutron dia ialah 1.006. Dia ada value dia. Kalau proton 1.007825. Tengok cara dia ambil. Neutron ialah 1.008. 665. Okay, U. Unit ialah U. So kita kena kalilah 3 kali dengan ni. Okay, kali dengan ni, tambah dengan 3 kali dengan yang ni. Tambah yang tu, okay, dapat dia punya value, get that value, and then you try to compare it with the, not just compare, but you need to find the difference, which is 6.05, 6.015122. Okay, so you need to add, we need to minus with this kind of value. So with that things, now you can get delta M. So the delta M, okay, so delta M now, okay, is equivalent to that C square. What is the value of C square? C square is M electron volt over U. So M tadi value dia ada U, kita potong lah dengan UM tadi. So in the end kita tinggal jawapan dia MEV, M mega electron volts. Okay, sekejap saya tengok ada soalan. What is the difference between atomic mass and chemical atomic mass? Okay, Syazani Nabil Tan. Okay, in my terms of atomic mass is the number of protons. Okay, in the chemical atomic mass, I didn't know. Okay, so please bila kita cerita pasal atomic mass yang ini, which is Z number, ialah merujuk kepada proton number. Okay, alright. Okay, now look.
Example 29.1, the binding energy of the deuteron. The nucleus of the deuterium atom called the deuteron consists of a proton and a neutron. Calculate the deuteron's binding energy in megaelectronvolt given that its atomic mass, where the mass of the deuterium nucleus plus an electron is 2.014102. So we want to calculate the binding energy of this deuteron. So how do we do that? Because we know that in the case of deuterium, right, deuterium-2, we have one proton and one neutron. Right, so the proton is starting from here, number of proton, and the number of neutron is the difference between the E and Z. 2 minus 1 is 1. So that means we have one neutron. So we want to find the mass of the proton and neutron it contains first. Right, so we want to find the mass of the proton and neutron it contains. So we have one proton and one neutron. So by referring to the table, we know that one proton has the mass of 1.00785. Right, so this is the mass of the proton. It is referring to the hydrogen 1,1 because hydrogen is only having one proton and 0 neutron. So this one is equivalent to the mass of one proton, which is 1.0078252. And the mass of the neutron is given in the table, which is equivalent to 1.008665 U. Right. So we have the mass of the proton and neutron it contains. Right. So add them up, and then we have to minus with the mass of the nucleus itself. The nucleus in this case is deuterium, and deuterium has the mass of 2.014102. Is also given in the question, right? So you find the difference, which is delta M, and then once you found that, you multiply it with the C squared, which is equivalent to 91.5 mega electron volt per 1 U. Then you can get the binding energy where the unit is in mega electron volt.
Okay, so this is the good examples on how you can find the binding energy. Okay, the binding energy of the deuteron. What is the deuteron? The nucleus of the deuterium atom. Deuterium atom is H21. Okay, H21. Okay, meaning that the isotope for hydrogen. Okay, hydrogen normally 1,1. So this is the deuterium means hydrogen with another additional neutron. Okay, so the value will be the last answer will be 2.224 mega electron volts.
As an exercise, you can try to do this question. Find the binding energy and average binding energy per nucleon on magnesium 24. Right, so you need to find the binding energy and also the average binding energy per nucleon. So this is the solution. You can discuss this solution with your respective lecturer.
Okay, look, this is the exercise. Okay, that is Madam actually talking about. So finding the binding energy, the average binding energy per nucleon. Okay, so first of all, you need to find the proper binding energy. So now we have magnesium 2412. Okay, magnesium 2412 is based on proton that is 12 and neutron that is also 12. Okay, so the 12 proton plus with the 12 neutron, you add up everything, you get 24.19788. That you don't simplify that value. Make sure you take every decimal point. Take everything. Okay, don't simplify the value. If you simplify the value, you cannot get the right or the correct answers. And mass of the magnesium will be 23.95985042. Okay, slightly different compared to this. And now you need to minus, okay, but regardless of the equations, okay, nampak kat sini yang kecil tolak yang besar ataupun besar, yang mana satu tolak yang ni initial, yang ni final kan, kita tak kira macam tu. Yang penting E is equivalent to delta M C square. Okay, delta M C square. Remember, we have modulus. Don't bother about negative or positive of the delta M, because it should always be positive value, because we are now calculating the energy. Okay, doesn't comply with any vectors. So this is the energy. And remember, the last unit will be mega electron volt unit too. When you have the difference between delta, the mass, and you need to calculate, you need to times with the 931.5 mega electron volt over U, because this one U, you can cancel out U and U, so you left with this, but the value will be 198.26 mega electron volts. Okay, all right. So let's do some calculations. Let's say you have 24 times 8, and you will get 2, 3, 19 something, 6, 192. Okay, all right. So let's say if you want to calculate the second question, which is the average binding energy per nucleon, then you need to use that kind of value, and then you get, you have to E this value, and you divide with the mass number. The mass number will be 24. So divide with the 24, now you will get to the 8.26 mega electron volt per nucleon. Sometimes they will ask you in terms of average binding energy per nucleon. Okay, so that nucleon number is based on Z plus A. Sorry, Z plus N. Okay, atomic number plus neutron number. So you will got nucleon. Okay.
29.6 nuclear reactions. Structure of nuclei can be changed by bombarding them with energetic particles. The changes are called nuclear reactions. For example, when alpha particle collides or strikes nitrogen, it releases hydrogen. So the process can be represented by this reaction, right? So as with the nuclear decays, the atomic number and the mass numbers must balance on both sides of the equation. For example, let's say in the case of this, when the alpha particles collides with the nitrogen, the mass number before the nuclear reaction is 14 plus 4, which is 18, right? So after the reaction, it releases hydrogen. So basically it's 1. So we want to get this unknown nucleus. So how do we want to get that? So 14 plus 4, 18 minus 1. So we will get 17 for the mass number of the unknown nucleus. And then for the atomic number, 7 plus 2, which is 9, minus 1, right? So basically we will get 8 as the atomic number for the unknown particle, right? So if you take a look at the table, right? So 17.8 is actually referring to oxygen. So this is the complete reaction. So basically, if you take a look at this nuclear reaction starts with 2 stable isotopes, right? Helium and nitrogen, and produces 2 different stable isotopes, which is hydrogen and oxygen.
Okay, so this is the nuclear reactions of what does it mean by nuclear reaction? Meaning that we should always the number of atomic mass and the atomic number and mass number must balance on both sides of the equations. Like I did just now, whenever Madam said 14 plus 4 and then minus 1 is why? Because we want to find the daughter part. Okay, that's all. Right.
Nuclear radiations has a lot of applications. In medical field, for example, it is being used in sterilization of the medical equipment, and it is being used to destroy bacteria, worms, and insects in food. It also can be used as tracers, and also it is being used in the magnetic resonance imaging to detect diseases.
Okay, that will be the applications, medical, in terms of medical. Okay, very good. Okay, so this should be the next slide.
At the end of this lesson, you should be able to describe the concept of nuclear fission, nuclear fusion, and describe fission concept to unstable nuclei. 13.1 Nuclear fission. Nuclear fission occurs when a heavy nucleus splits into two lighter ones, especially after capturing a neutron. So a heavy nucleus is like uranium, right? So uranium is a heavy nucleus. It itself is unstable. So once it captures a neutron, it becomes more unstable, right? And when it becomes more unstable, it will be excited, right? And then it will undergo nuclear fission, where this unstable nucleus, right, will be split into two daughter nuclei, which is more stable, and this lighter nucleus do not need so many neutrons. So there are typically extra neutrons emitted from the reaction that can lead to a chain reaction. Okay, so let's take a look at this process first. So basically, with each process of this nuclear fission, it will create more neutrons. Right. So this is the process. Right. Uranium captures a neutron. So in a split second, right, it will be an excited nucleus, and then it will undergo nuclear fission, right, where it will be split into two daughter nuclei and some additional neutrons. So imagine if this additional neutron that is being generated, right, from the first nuclear fission process, right, so this neutron that is being generated collide or be captured by another uranium, what will happen? More neutrons will be generated, and those new neutron will be captured by another uranium, and so on, and it will actually generate a massive amount of energy, right? So this is what we call by chain reaction. So for example, when
Okay, I think it's clear enough. So fission, now we have two things. We have fission and fusion. Okay, fusion means combine, fission means splitting. Okay, split. Okay, right. So when combines, when they want to split, is based on heavy nucleus, it splits into two lighter ones. So the daughter nucleus here to be recorded as lighter ones. Okay, it creates a lighter daughter nucleus. Okay, but from where? From the excited nucleus. Okay, remember, first of all, it have a heavy. It contains a heavy nucleus. When one neutron happens to be bombarding this heavy nucleus, what happens, it becomes excited. That's why, okay, I'm start giving some aura kat sini, okay, to show that, okay, this nucleus is excited, right? And whenever is excited now, it will reduce. In order to them to be stable, it will emit, okay, a two daughter nucleus that is stable. Okay, two daughter nucleus together with another neutrons. So another neutrons is formed at this side. So it can cause a chain reaction. Maksudnya benda ni akan jadi berantai. Daripada satu neutron boleh jadi, contoh dia dalam kes ini dua neutron. So bayangkan yang ni pula langgar heavy nucleus yang lain, dapat lagi dua. So from 1 you get 2. Now from 2 you get 4. From 4 you get 8. From 8 you get 16. From 16 you get 32. From 32 you get 64, for example. So that will cause you chain reactions. Okay, so this is.
For example, when a uranium-235 captures a neutron, it may undergo the following fission reaction. So uranium-235, it captures a neutron, it will be heavier and becomes more unstable, uranium-236, temporarily, and then it will be excited, right? And then it will be going to nuclear fission, right? Where it will be broken into two daughter nuclei, and in this case, it releases 12 neutrons. So these two daughter nuclei, one of it is strontium, right? Strontium-88, and another one is white, which is an unknown nucleus. So the question asks us to complete the reaction. That means we need to find this unknown nucleus, which is white. So because we know in the case of nuclear fission or any nuclear reaction, right, the basically, before the nuclear fission, the mass number is 235 plus 1, which is 236, right? And then we want to get this unknown. So how do I get that? So 236 minus 88 minus 12, so we will get 136 for the mass number of the unknown nucleus. And then for the case of atomic number, before nuclear fission it was 92, so after the nuclear fission it becomes 38, right? Then so you get 92 minus 38, so basically the atomic number for the unknown nucleus is 54, right? So 13654, if you take a look at the table in the appendix B, right, you will know that the unknown particle is actually, or the unknown nucleus is actually xenon. So that completes your nuclear reaction, right? So this is the reaction. And then the question asks to determine the energy released, right? So basically, the energy, in the case of energy release, we are going to use the equation of E is equivalent to delta mc squared. So where delta m is the energy before minus the energy after the nuclear fission. Why? Because the energy before is greater than the energy after. So if you take a look at this process, right? So if you take a look at this process, you will see that before it has uranium-235 plus 1 neutron, and after it has strontium-88 plus xenon-136 and 12 neutron. So how do one calculate the delta M, right? So basically at the left side of the equation we have 1 neutron, at the right side of the equation we have 12 neutrons. So basically we actually can cancel this out, right? So this one can be cancelled with this, so this one becomes 0 and then this one becomes 11. So with that, you can calculate the delta M, right? So delta M is before, now it's left with the, once we cancel it out, so we are left only with the uranium-235. So you take a look at the table in appendix B, uranium-235, this is the atomic mass unit, right? Minus, after the nuclear fission, we have strontium, so xenon, and left with 11 neutron, because we already cancelled it out previously. So minus 11 neutron, right? Minus the mass of the strontium and minus the mass of the so you get your delta M, the delta M for this process, right? So we get in the delta M, right? And then multiply that with C squared. Multiply that with C squared. So basically, when you multiply with C squared, right? So you will get the energy released by this nuclear fission process. So the nuclear fusion process in the sun begins with 2 protons fusing to form deuterium and then fusing with the third proton to form helium-3. So for example, let's say in the case of this, we have this hydrogen, right? Fusing with another hydrogen and forming the hydrogen to 1, or another name for it is deuterium, right? So because the right hand side and the left hand side of the equation should balance, so it's supposed to be, however, we don't have any nucleus which is 2, 2, so we only have 1. So 2, 1 is deuterium, and that means it emits together positron as well as the neutrino, right? And then this deuterium then fusing with a third proton, right? So this deuterium fuse with the third proton, which is hydrogen, to form helium and gamma. So after that, helium-4 nucleus is formed in one of the following ways. So this process of each of these nuclear fusion process will emit a considerable amount of energy. So for example, example 3.2, find the energy released in the reaction of helium-3 with deuterium. So we have helium-3 and deuterium, and then becoming helium-4 and hydrogen. So we want to get the energy generated, right? So we know that E is equivalent to delta M C squared. difference of energy before and after nuclear fusion. Right? So the energy before is greater than the energy after the nuclear fusion. So we get the mass of the helium-3 plus mass of the deuterium, right? Which is this one is before, this one is after, right? So the mass before minus the mass after. So mass of helium-3 is 3.016029U. Mass of deuterium is 2.01410U minus mass of helium-4, which is 4.002603U, and minus the mass of hydrogen, which is 1.007825U. So all these value can be obtained from the table like what I've shown you previously, right? So you will get your delta M. Once you got your delta M, multiply it with the C squared as per normal, right? And then you will get the amount of energy generated from this process.
Okay, so that will be the last subtopics. I think the last topic for PHY 098, the nuclear fission and nuclear fusions. Okay, so that will be it. So I think you should always do some revisions in terms of that. That don't worry about the appendix, because appendix will be there. Okay, sometimes they don't give you a sheets of appendix, but they put that value here besides your questions or whatever, but they will give you. And the idea is you need to write down every decimal point without missing anything. Okay, without missing any decimal point, you need to put every points, because that will although one or two decimal points missing, it will give you different kind of values. Okay, all right. Any more questions? Any questions? Do you have any questions? Oh, you have any questions? Okay, I have from Hamiza. So for mass proton use, should we refer to appendix survey or list formulas? Because both value lain-lain. Yes. Anything regarding appendix, okay? Anything regarding appendix, please refer to whatever you have for the official one. Okay, so as for now, the official will be based on the questions. Maksud dia soalan keluar akan di-provide terus dengan appendix tersebut. Okay, jangan tengok mana-mana lah, kena tengok kepada soalan. Okay, I will consult my colleague so that the atomic mass unit yang sepatutnya value dia berapa. Kalau untuk proton untuk proton, sebab memang betul ada dua value yang berbeza. Saya perasan di bahagian belakang tu ada berbeza. Of course, some taken from another book, some from the survey books. Okay, and I think we need to use our textbook, which is the survey books, to confirm it. Okay, but as for now, you can say that all the atomic mass unit must be provided with the survey appendix. Okay, kena guna survey dulu. Any more questions? Okay. For these two topics, right? Okay, apa dia soalan dia? Jawapan dia ialah definitely. Okay, X. Okay, X is our element. Okay, X, A, Z. A mestilah mass number. Okay, what is mass number? Mass number ialah A. Okay, A which is Z plus N. Z ialah atomic number. And N ialah neutron number. Okay, so the answer should be D. Okay, mass number, atomic numbers, and also X is element. Okay, choose the correct answers. Okay, question number 2. Number of neutrons in the nucleus is Okay, you have A, the divisions of mass number and atomic number. Okay, division of mass number, kalau kita tengok sini, A bahagi dengan Z, betul ke? Kan? Salah. Salah. The difference between mass number and atomic number. So mass number A tolak dengan atomic number. So mungkin betul. So A, B, C, the multiplication of mass number and atomic number, salah. Okay, and D, the total of mass number and atomic number. The total of mass number and atomic number. So jawapan dia B. Okay, number 3, the elements that have same number of protons but different number of neutron is known as definitely isotopes. Okay, for example, you have carbon 14 and carbon 12. If you refer to the periodic table, you can see carbon is 12. The mass number is 12. Kan? So tapi kalau kita dalam fizik kita ada carbon 14. So maksudnya ada 2 lebihan neutron dekat situ. Biasanya dia punya atomic number is 6. Okay, so atomic number 6. So kalau dia ada carbon 14, 6, maksudnya neutron dia ada lebih 2. So itu ialah dipanggil isotope. Kita dah tahulah kalau fusion, fission, twin ni semua satu yang bukanlah, kita dah faham. Fusion ialah penggabungan, fission ialah split. Okay, we use the unified mass unit. Okay, U, because it's defined from, okay, apa dia kaitan dia? So A, the mass of one element of the isotope C12 atau carbon 12, which is exactly 12U. The mass of one electron of the isotope, okay, carbon 12, which is exactly 12U. Okay, the mass of one atom of the isotope will be carbon 12, which is exactly 12U. The mass of one neutron, okay, one neutron of the isotope, which is exactly 12U. So the answer will be C. Okay, why? Because the mass of one atom of the isotope. So we are not going to discuss about mass of neutron, mass of electron, or mass of the element. Instead, we use mass of one atom. Okay, mass of one atom, which is carbon 12 is exactly 12U. Okay, blank. And number 5, the blank is the energy that must be added to a nucleus to break it apart into its separated. Break, okay, split. Jawapan dia apa? Mesti apa tu? Okay, so lu tak habis baca lagi. It's separated neutrons and protons. Definitely apa dia? Binding energy. Because binding energy, we want to calculate the energy to break the proton and the neutron from the nucleus. Ingat, ada nucleus, selalu kena ingat macam ni. Nucleus, okay, kita nak buang proton, kita nak buang neutron dalam ni. So kita kena tahu dulu what is the energy of the proton and neutron, and also energy of the electron, nucleus. So that's what we call as binding energy. Okay, half-life is called the decay constant, and it determines, okay, apa maksud dia? Determines. So kita ada beberapa jawapan. The time at which the material will decay, the rate at which the material will decay, the number of nuclei in the sample, the activity of the decay process. Okay, decay constant. Kalau kita tengok equation dia, N equals to N naught E exponentially half-life kali dengan T. Ini dia punya equation dia. Okay, so kalau kita tengok dekat situ macam mana lambda ini dinamakan decay constant. Right? So what is the decay constant? Is kalau kita tengok dekat sebelah dia tu ada T. Okay, dan kalau kita tengok daripada graph of N bahagi N naught dengan saya tak ingat apa kat bawah ni, time. So kita akan dapat equation, kita akan dapat macam ni. Okay, so lambda yang dekat atas ni ialah paling sikit, dan semakin dia akan lagi besar. The decay constant will be greater. Okay, semakin lama semakin besar. So that means dia ada kaitan dengan rate, dengan time. Okay, so kalau kita gunakan time tak sesuai because it must be the rate at which the material will decay. Jawapan dia B. Right? Move to the next part. Choose the correct answers. Okay. Tu tak nampak dekat situ sepatutnya dia tulis dekat sini apa ni, ini elektron. So this is electron ni elektron, yang ni ialah positively charged nucleus. Positively charged nucleus. Okay, and figure 2 kita ada nucleus yang positif ni nucleus, and ni ialah elektron. Okay, so kita ada beberapa jawapan dekat sini. So we have maybe jawapan A. So Rutherford's planetary, figure 1 ialah Rutherford. Okay, kalau kita nak faham, kalau elektron dengan positively charged nucleus ni, ini kita boleh katakan macam seolah-olah watermelon. Okay, plum pudding. Kadang-kadang dia panggil watermelon, kadang plum. Tengok buku juga. Plum pudding. So dia anggap electron is like a tiny particles that contain inside the positively charged nucleus. So ini yang tak lain dan tak bukan, mestilah ialah apa nama dia tu Okay, biasanya kita namakan dia Dalton. Atom Dalton kan, Dalton. Okay, tapi kalau dalam kes ini, okay, apa nama dia, saya pun dah lupa. Tetapi definitely, okay, ini jawapan yang betul dia, definitely, okay, figure 2, alright, figure 2 merujuk kepada Rutherford. Figure 2 merujuk kepada Rutherford because Rutherford saying that the electron is orbiting the nucleus in the middle. Itu Rutherford beritahu a planetary model. Seolah-olah elektron itu ialah a planet yang mengorbit, yang ada orbit. So itu ialah jawapan yang tepat. Jadi untuk soal jawapan ini, okay, so yang paling sesuai ialah C, which is Rutherford. Okay, so ini ialah Thomson's model of an atom. Kita ikutlah dia kan. So sebenarnya is Thomson's model of an atom. Saya ingat Dalton tapi sebenarnya Thomson's model of an atom because we want to get the answers for the figure 2 because figure 2 is exactly for Rutherford's planetary. Nampak ni ayat dia, planetary models. Kalau planetary memang untuk Rutherford's. Okay, according to Bohr model, which of the following is incorrect? Okay, kalau dalam exam tolonglah underline this incorrect. Maksudnya dia nak jawapan yang salah. Dia nak jawapan yang salah, bukan nak jawapan yang betul Okay, kita baca dulu. Electron move under the influence of Coulomb force of attraction. Betul. Only certain electron orbits are stable and allowed. Yes, this is a Bohr postulate of models. Diberitahu oleh Bohr. Okay. Electron release energy when shifting from excited state to ground state. This is also correct. And the electrons revolve around the nucleus in fixed circular orbit. Ini tak berapa tepat ni. Electron revolve around the nucleus in fixed. Adakah in fixed circular orbit? No. That will depends on the nucleus itself. Ada nucleus besar, dia punya orbit dia besar. Ada nucleus kecil, orbit dia kecil. So it's not a fixed circular orbit. So definitely jawapan dia salah. Jawapan dia D. Okay. So 1, 2, 3 until 8 cukup untuk jawab ABC. Alright. Match the following statement accordingly. Match of the following. Dia ada bagi beberapa pilihan jawapan tu. Saya nak tengok soalan asal dia apa. Dia ada bagi alpha decay, beta decay and gamma decay. So which one yang represent those states? Okay, kita tengok dulu. When nucleus undergoes this type of radioactive decay, the daughter nucleus has the same number of nucleons. Dia nak tipu ni. But the atomic number is changed by 1. Okay, nucleons merujuk kepada Z campur N. Okay, daughter nucleus has the same number. So Z campur N ni ialah apa? Ialah mass number. Okay, ialah A. Okay, so the answer for this type zat lain dan tak bukan mesti merujuk kepada beta. Okay. Because dia akan keluarkan elektron ataupun positron. Sebab tu dia kata dia tak cakap pun kurang satu ataupun lebih satu. Sebab dia kata atomic number is changed by 1. Sebab tu maksud dia. Right, for number 2, nuclei are often in an excited state following radioactive decay and they release their extra energy by emitting a high energy photons. Okay, so itu memang merujuk kepada apa? Kalau kita baca, dia mention mengenai excited state. Okay, excited state ni definitely untuk beta dan juga untuk gamma sahaja. Beta dan gamma saja. Tapi kalau dalam kes ini memang dia kata release extra energy. Tadi madam tu mention tadi is considerable high energy by emitting a high energy photon. So definitely this one goes to gamma rays. Gamma decay. Okay, so lastly, okay, radioactive decay in which nucleus emits an alpha particles. Dah tengah-tengah alpha kat situ. So this one is the alpha decay. Alright. Okay, now we go to the problems and solutions. Okay, we have chapter 28. Okay, chapter 20 ini yang lepas kita tengok yang daripada minggu lepas. A photon is emitted when a hydrogen atom undergoes a transition from n equals to 5. Okay, a photon is emitted when a hydrogen undergoes a transition n equals to 5 state to the n equals to 3 state. Calculate the wavelength, the frequency and the energy and in electron volts of the emitted photons. Okay, when it calls about photons and dia ada bagi state, dia ada bagi orbit ataupun when it mention satu, dia gunakan hydrogen atom. This is hydrogen atom. Okay, look at the hydrogen atom. So hydrogen atom ni kena ingat dia ada satu Rydberg equation. What is Rydberg equation? 1 over lambda is equivalent to Rydberg constant times with 1 over n square minus with 1 over m square. Itu cerita dia. Okay. Dan dalam situasi ini kita akan gunakan Rydberg constant which is n equals to 5 and n equals to 3. So in this case, right, so kita akan dapatkan n yang pertama, mesti n yang duduk di depan lah, was because yang besar kena tolak yang kecil kan. So 1 over 3, so dia 1 over untuk A, 1 over lambda is R, okay, 1/3 square tolak 1/5 square. So dekat sini kita masukkan dia punya R Rydberg constant, berapa value dia? 1.097 times 10 power of nampak value je. Power of 7. Okay, 10 power of 7. Okay, so dapatkan tu. Don't forget bila masuk dalam ni kena reciprocal balik. Reciprocal balik sebab dia 1 over lambda. Lambda sini kita dapat, okay, lebih kurang jawapan dia 1.281 times 10 power of negative 6 meters. Okay, boleh tinggal jawapan dalam ni ataupun kalau rajin boleh tukar dia dalam bentuk nanometers. Biasanya wavelength ni nanometers lah. Okay, but tak apa. Okay, just leave the answers in 10 power of negative 6 meters. Okay, so B the frequency. So the frequency is based on, okay, one we have lambda. So V equals to F lambda. F is equivalent to V over F. So V ini ialah C. Okay, which is mean kalau main dengan at the atomic level, we use the speed of light. So in this case, speed of light adalah 3 times 10 power of 8 divided by wavelength. Terbalik tadi. Ni wavelength wavelength. So masukkan value ini tadi kat bawah ni, So dapat jawapan akhir dia frekuensi ialah lebih kurang 2.34 times 10 power of 14 Hz. Okay, now we move to the question C, the energy in electron volts of the emitted photons. The energy. Okay, so the energy of the emitted photons E equals to HF. Masih ingat lagi? Okay, this is using Planck's constant, which means Hc over lambda. So we can use H is a Planck constant. Ataupun nak guna F terus pun boleh. Okay, Hc 3 times 10 power of 8 kali dengan lambda dia 1 yang ni, lambda yang ni masuk sini. Okay, but dia nak jawapan dia dalam electron volts. Okay, nak jawapan dalam electron volts. So jawapan dia nanti, okay, nanti jangan lupa kalikan dengan 1 electron volts, which equivalent to 1.6 times 10 power of negative 19 joule. Yang daripada sini tadi dapat, daripada yang ni dapat joule. So joule akan potong dengan joule bawah ni. So yang ni dapat 1 electron volt. Jawapan akhir dia 0.970 electron volts. Okay, so the key words untuk soalan ini ialah hydrogen atom. Hydrogen atom. So bila kita nampak ada hydrogen, patut ada N tu, kamu boleh masukkan dalam these things. Okay. Ini daripada N5 pergi kepada N3. Ingat, daripada tinggi kepada turun dia akan release energy. The next question. Find the radius of the nucleus of helium-42 and also the uranium-23892. Okay, this one kena gunakan equations. Saya pun lupa equations. Sekejap, saya lupa sekejap. Equation dia ialah for 2 helium, okay, we have proton, berapa tu? Proton ada 2, neutron ada 2. Okay, neutron ada 2 juga. Jadi untuk equation dia R is equivalent to R naught. Ni radius dan radius of the nucleus kali dengan A, atomic mass unit 1/3 A. Okay, ataupun a square root of cubic root of A. Okay, so dekat sini R naught tu ada satu value 1.2 times 10 power of negative 15 meters. Ni satu value yang sama 1.2 10 power of negative 15 meters kali dengan A. A untuk helium-42 ialah 4. So jawapan akhir dia ialah 1.9 times 10 power of negative 15. Sebab itulah negative 15 ini ialah Fermi. Okay, kalau ada 1.9 FM. Okay, untuk B pun sama. Uranium 23892. So dia punya A dia ialah 238. So dekat sini R equals to R naught A 1/3, which means R naught 1.2 kali 10 kuasa negatif 15 kali dengan 2, 38, 1/3. Jawapan akhir dia ialah 7.4 times 10 power of negative 15 meters. Ataupun 7.4 Fermi meters. Okay, ini equation dia. Okay, try to check your appendix balik. Kalau ada, okay. Kalau tak ada, then you need to memorize. Senang je R equals to R naught. R naught itu ialah constant value. A ialah our mass number. Okay, the atomic mass of oxygen is 15.999 U. Convert this mass to units, a kilogram and also mega electron volt over C square. So how to do that? Right, so now we have mass. Okay, mass is equivalent to 15.999 U. Okay, convert this mass to, first kita so convert kepada kg dulu. Macam mana convert kg? So 15.999 remember, kali dengan 1U equals to berapa? 1.66 times 10 power of negative 27. Ini atomic mass. 27 kilogram. So U dengan U potong, dapatlah dalam unit kilogram 2.66 times 10 power of negative 26 kilogram. Okay. And part B, so this is part A. So the part B wants you to calculate using the mega electron volt over C square. So remember, M is 15.999 U. So what does we do? What should we do? So 15.999 U times with 931.5 mega electron volts. Okay, over C square is equivalent to 1 U. So dapatlah matikan dia. Dapatlah jawapan dia 1.49 times 10 power of 4 mega electron volt over C square. So kalau ada soalan, please let me know if you do have a questions, please let me know. Okay, because I cannot see you from this view. Okay. Okay, next is number 4. Find the average binding energy per nucleon. Okay, this is a good question. Tadi kita dah buat kan macam mana nak dapatkan yang 2412 magnesium tadi daripada tu kan. Macam mana dia dapat? Okay, kita cuba dulu. So now average and binding energy per nucleon. So now we have magnesium 2412, meaning that proton dia ada 12, neutron dia pun ada 12. Okay, so you need to find the average binding energy dulu. So average binding energy of the neutron ialah, kita dapatkan tadi berapa, saya tak ingat jawapan dia, 19 something jawapan dia, tak silap Okay, but the idea is you need to do it, okay, with the helps of appendix. Dalam soalan ini kena gunakan appendix. Right, so in order to calculate the energy binding, so EB, energy binding is what we call as summation of delta M C square. E equals to delta M C square. So what is delta M? Delta M kita kena ambil dulu. Okay, 12 proton plus 12 neutron, okay, minus dengan M, macam mana cakap? Okay, so mass, first mass of 12 proton plus dengan mass of 12 neutron, okay, tolakkan dengan mass of the nucleus 24. Okay, nucleus of magnesium 24. Okay, so hasil daripada ini, okay, don't worry, okay, kita akan kalikan dengan mega electron volts over C square kali dengan 1U. So dekat sini jawapan dia dalam U dengan U akan potong. So tinggal jawapan dia mega electron volts over C square. Okay, mega electron volt over C square. And yang ni kita dah gantikan dengan C square tadi. So dia dah jadi mega electron volt sajalah. So jawapan akhir nanti ialah mega electron volt. So bila kita nak buat energy binding per nucleon, EB over A. Masukkan dia punya mass number. So jawapan dia nanti dapatlah 8.26 mega electron volt per nucleon. Dimension per nucleon. Okay. So untuk soalan yang kedua pun sama, tapi dekat sini saya tidak ada jawapan. Okay, saya buat separuh jalan lah. Right? Because we have P, which is the rubidium, okay, 85 and 37. So proton dia ialah 35, neutron dia ialah have 48. Okay, 48. So you need to find the mass for maksud dia mass untuk rubidium ni nanti dia akan jadi E equals to delta M C square. C square tadi je ialah mega electron volt. So dalam ni dia kita akan tolak macam mana. So mass of the proton 35, okay, plus dengan mass of the neutron 48 minus with the mass of the rubidium 85 kali dengan mega electron volt over 1U. So jawapan nanti U dengan U potong, so tinggallah jawapan dia dalam mega electron volt. Tapi itu untuk E Lepas tu untuk dapatkan E per A, so jawapan E tadi bahagi dapatkan A, so jawapan akhir dia 8.70 mega electron volt per nukleon. Remember to put per nukleon. Tapi ini memang kena gunakan appendix. Yang saya akan bulatkan ni semua ni appendix. Kena refer kepada appendix. Ada value-value dia. Saya tak. Ya.
A tu dapat dari mana?
Macam A ni lah. Mass number lah.
Oh, mass number.
Kan elemen kita. Ni lah. 85, 24 tu A dia.
Thank you, sir.
Bagi je. Okay. Dapat jawapan mega electron volt bagi dengan A. Okay, now we move to another questions. Questions number 5. A drug tag with the 9943 Tc, which is half-life is 6.05 hours, is prepared for a patient if the original activity of the sample is 1.1 times 10 power of 4. Bukan 104 ni, 1.1 times 10 power of 4 becquerel. What is its activity after it has been on the shelf for 2 hours? Okay, for 2 hours. So dalam kes ini kita kena gunakan equations kita lah. Okay. Apa equation tadi, lupa lah. Okay, so for this case, in becquerel, R equivalent for R naught, okay, E, which means lambda, negative lambda T, ada log 2, sekejap. Okay, R equals to R naught epsilon kali dengan negatif 1 over half-life kali dengan log 2. Okay, ini ada equations. Tapi saya tak sure equation ni ada dalam appendix awak ke tak, tapi ini saya dapatkan daripada buku equation ni. So untuk dalam case ini, alright, so this is activity menggunakan unit becquerel. As we know, this is the radioactivity. Okay, activity untuk yang menghasilkan half-life. So half-life untuk case ini ialah 6.05. Okay, 6.05. T kat sini, T over lambda. Okay, T over lambda, which means now, alright, okay. So untuk case ini, R ini yang kita nak cari ya. The activity is R. So the R naught here is 1.1 times 10 to power of 4. Bukan ni salah typing Kalikan dengan epsilon Okay, dalam kurungan 2 hours because it has been on the shelf for 2 hours. So that will be the remaining time. Okay, the remaining time 2 hours. The half-life is 6.05 times with ln 2. Okay, so you punch your calculators. Remember this one dia duduk dalam exponent yang belah atas ni duduk dalam exponent. Okay, so you need to use exponent untuk dapatkan 8.7 times 10 power of 3 becquerel. Okay. Okay, so but please everybody need to check this equation. Okay, need to check this equation. Either dia ada ke tak dalam your appendix. Okay. Okay, next we go to the next questions. Alright. A freshly prepared sample of a certain radioactive isotope has an activity of 10 millicurie. Ci stands for curie. Okay, curie ya, C-U-R-I-E. Tapi dia punya short form ni adalah Ci. Okay, after 4 hours, the activity is 8 millicurie. Find the decay constants and half-life of the isotopes. Okay, decay constants and half-life of the isotopes. So how to do that? Right. So in this question, we have 4. Yeah, this is the activity. This is the time, 4 hours, and we have the decay constants. The decay constants. The activity of 10 and also 8. Okay. So first of all, we need to get the n value. Okay, the n value, which means we need to use that equations. R equals to R naught epsilon of T over lambda times ln 2. Okay, so because we have half-life. Okay, half-life. The half-life is equivalent to T ln 2 over T. Half. Okay, the decay constant is ln 2 over half-life. So this should be your half-life. Okay, so macam mana kita nak masukkan ke dalam equations tu tadi? So first of all, dia nak suruh cari find the decay constants and half-life of the isotopes. So dia nak suruh cari lambda. Okay, dan juga dia nak suruh cari yang ni. Maknanya once kita dapat lambda, kita akan dapat yang ni pula. Sebab lambda, bila lambda dah dapat, nak dapatkan half-life, it's just a matter of ln 2 divided with lambda. So we need to find what is lambda. So kita rearrange the equations so that we will get equation yang sesuai dipakai ni. Okay, maksudnya dia rearrange, bila kita rearrange the equation ini, dia akan dapat that lambda is equivalent to, the decay constant is equivalent to negative ln of R over R naught divided by, okay, ln divided by T. Okay, divided by T. Okay, so macam itulah dia ln kan kedua dia dua-dua belah ni dia ln kan dulu. So dia ni R bawa pergi ke bawah. Okay, so dua-dua belah dia ln kan, and the end dia akan dapat macam ni lah. Okay, dia simplifykan yang ni so that kita dapat lambda is equivalent to negative ln R bagi R naught ialah 0.8 berapa tadi, 10 R R naught ialah 8. Okay, bahagi dengan apa masa dia tadi, 4 hours. Semua dalam SI unit, 4 hours. So in the end, the lambda will be daripada 5.58 times 10 power of negative 2 hour. Okay, hour per hour. Negative 1. Okay, so that will be the lambda. Lambda ni bukan wavelength tapi dia adalah decay constant. Okay, decay constant. So once kita dapat decay constant lambda, kita masukkan dalam equation dekat atas ni untuk dapatkan half-life. Ln 2 divided by 5.58 times 10 negative 2. So you will get, tapi kena ingat ini dalam bentuk hour. So jawapan kita nanti semua dalam bentuk hour. Untuk half-life, dia depends kepada situation. Kadang-kadang dia dalam days, kadang-kadang dia dalam bentuk minit, kadang-kadang dia bentuk second. So kalau dalam kes ni dalam bentuk hour, so per hour lah. Right, so the answer for this question is 12.4 hours. Okay, how many? Okay, that is for soalan B ialah how many atoms of the isotopes were contained in the freshly prepared sample. Okay, how many atoms? Okay, macam mana jawab tu? So kita kena gunakan equation RO equivalent to dia ada satu equation, saya selalu lupa equation ni sebab jarang nak guna activity ni, but we need to calculate jugalah. So ini ialah A, so ini ialah B. Okay, so the N number, okay, the number of atoms, di asal dia ialah R equivalent to lambda N. Maksudnya lambda decay constant kali dengan atom. So N ialah R bahagi dengan lambda. R bahagi dengan lambda. So R itu kita ambil menggunakan R0, which is kena ada satu sebab dia beza millicurie MCI ini dengan becquerel. Okay, becquerel tadi which is kita ada satu beza dia lah kan, which is R0. Okay, dekat sini 10 times milli 10 power of negative 3 Curie is equivalent to, tapi bila Curie dalam kes ini dia nak suruh kita cari dalam atoms. Okay, dalam atoms maksudnya kita kena buang semua value yang millicurie ni. So dekat atas, so 1 millicurie, 1 Curie is equivalent to 3.7 10 to the power of 10 second negative 1. Okay, maksudnya dekat atas ni ada second negative 1 divide by lambda. Lambda pula adalah hour, which is 5.58 times 10 power of negative 2 hours. Hours tu duduk di sebelah atas kan, tapi kita nak supaya second dekat atas tu dengan second kat bawah ni, so we need to, so dekat sini dia sebenarnya per hour, so 1 hour over 3600 second. Okay, 3600. So ni boleh potong, dekat bawah ni kita bahagi siap-siap 5.58 divide by 3600, and then in the end you will get 2.39 times 10 to the power of 13 nuclei. Okay, alright, so tadi kita dah dapat dua jawapan, lambda which is decay constant, half-life, dan you gunakan equation ini. Okay, R ialah activity, to be exact the RO, dia punya original which means 10 millicurie, which means macam mana nak dapat RO tu, number of atom kali dengan decay constant. Okay, number of atom kali dengan decay constant. Alright, so dapat nuclei. Okay, and C, what is the sample's activity 30 hours after it is prepared? What is the sample's activity? So ini kita kena predict. Bukan predict lah, kena calculate sebenarnya menggunakan equation yang tadilah, which means we have R equals to R0 E lambda T. Tanpa ada ln lah, lambda T. So kita masukkan semua tu, cuma dekat time kita letak 30 hours. Okay, 30 hours. So in the end we will get, you see ya, masuk balik nilai R ialah berapa tadi, 10 millicurie R0 epsilon kali dengan lambda 5.58. Okay, 5.58 times 10 power of negative 2. Time dia kita gantikan dengan 30 hours, so dia akan cancel out time. So in the end you will get 1.9 times 10 power of negative 3 Curie. CI means Curie ya, untuk activity. Selain pada becquerel, kita kena guna juga Curie. Okay, right, so tak apa. Okay, just dulu apa yang ni, nanti kan kamu boleh study balik Alright, so now we look at the next lah. Ada tak berapa soalan lagi? 7, 8, berapa banyak lagi soalan. Okay. Find the energy released in the alpha decay 23892. The following mass will be the value, will be the useful. Okay. The thallium 23490 has a mass of 234.043583. Okay. Ini contoh, kalau tengok soalan nombor 7 is examples of how they give the answers in atomic mass unit ataupun they give the appendix. They don't give you the real appendix, but they give the value of the daughter nucleus. Okay, contoh ini kita tengok alpha decay. So uranium 23892. So when it happens, it undergoes the alpha decay. So you will get to the thallium, which is 23490s. Ingat kan? And then the plus dengan helium 42. Okay. So inilah cerita dia. So this is the energy release. Ini belum energy, ini baru dia reaction. Tengok all the values kiri dengan kanan semua akan balance. 92, 90 plus 2. So balance. Okay, so you need to find what is here. So this one is considered to be before. This one is after. So macam mana buat? E equals to delta M C square. So delta M siapa? Ya, kita ambil lah yang belakang ni, which is 234. Okay. Tak kisah pun macam mana pun. Yang penting kita akan tolak antara dua ni lah. So kalau kita tengok dekat sini, untuk dalam ni saja, untuk uranium dia punya atomic mass unit ialah 238.050783 U, tolakkan dengan thallium tadi tu 234.043583. Tengok saya ambil semua campurkan dengan helium. Helium ialah 4.002603 U. Tutup. Okey. Tutup sekali. Kali dengan mega electron volts over 1 U. Okay, so 1 U dengan 1 U ni akan dipotongkan. So in the end you will get lupa masuk sini 931.5. So in the end the answer is 4.28 mega electron volts. So that will be the energy release. Okay. Next we move to the next question. So the nickel with mass 659291 U undergoes beta decay to copper 6629. Okay, nampak dia tambah satu, maksud dia akan release elektron. Okay, dia release elektron dengan neutrino. Alright, so we start with the nickel. Nickel which is 6628. Okay, then undergoes a beta decay, so dia akan dapat copper. Dia dah bagi siap-siap 6629. Nampak dia lebih satu. Disebabkan apa? Sebabkan ada satu elektron. Which is elektron negative 10. Okay. Dia akan jadi kosong negative 1. And then neutrino lah. Neutrino tu kita tak calculate lah dia. So this is neutrino. Okay. And this is electron. Right. So macam tadi juga E equivalent to delta M C square. Apa-apa yang duduk dalam ni nampak tu, dia akan tolak dulu 65.9291 U, tolakkan dengan yang ni copper dia 65.9289 U plus with the berapa tu electron. But soalan dia ialah write the complete decay formula process. Okay, ini write the decay process. Okay, and then don't forget electron. Okay, electron doesn't have atomic mass unit. So kita hanya calculate guna yang depan ni je lah. Okay, so dia tak ada dia punya tu, kali dengan 931.5. 1.5 mega electron volt over 1U. So U dengan U potong. So dapat in the end jawapan dia 0.186 mega electron volt. So ini untuk part B, dia suruh cari kinetic energy maximum. So kinetic energy maximum samalah dengan energy. So 0.186 mega electron volts. Okay. The next one. Okay. Oh, sikit lagi. We have chapter 30. Okay, find the energy release in the fission reaction. Okay, boleh kat agak harap boleh nampak lah kot saya pun tak sekejap. Strontium ni macam tadi lah 235. Okay, so saya taruh sikit. Neutron 10 plus with uranium 23592. So you will get the fission of strontium 88 38. Okay, plus with xenon 136 54 plus with 12 10 neutron. Okay, so kalau kita tengok dia dah balancekan dekat kita, dia suruh cari the energy release. Ni boleh rujuk kepada apa panggil tadi lecture tadi 126 mega electron volt. Okay, macam mana dia calculated. Next. Okay, ini pun sama tadi ada dalam soalan tadi, find the energy release in a fusion reaction. Okay, fusion reactions. So sama juga. Now we have proton H11 plus with the deuterium 21. So you will get to the helium 32 plus gamma. Okay, find the energy release. Okay, so you need to calculate the E equals to delta M C square. So delta M siapa yang berada depan ni ialah initial, this one is the final. So siapa-siapa pun boleh tolak dekat situ. So jawapan dia nanti, okay, dalam ni kalikan dengan 931.5 mega electron volt over 1U. So 1U dengan U kat dalam ni potong, dapat jawapan dia 5.49 mega electron volts. So that will be the energy release. Sama juga. Okay, ni memang kena refer appendix juga. Okay, now we move to the additional questions. Okay, additional questions. Okay, untuk soalan additional questions ni, the age of any object made from non-living matter such as wood can be determined using the natural radioactivities of carbon-14. The technique is used by comparing a present activities obtained, okay, of a sample. Identify this technique. Okay, this is what we call carbon 14. Okay, dating ataupun radioactive dating. Okay, right. So number 2, complete the following decay processes by determining A, Z and X for each process. Okay, so dia ada dua soalan dekat situ. Satu dia suruh PO 214 dengan 84. Okay, satu lagi TL 210 dengan 81. Okay, so dekat sini dia bagi equivalent to apa baru nak masuk tu. Okay, 210 82. Yang ni lambung 210 82. So dia bagi X elemen A dengan Z. X elemen A dengan Z. Okay, so apa jawapan dia? Ini kita tengok yang belah atas tu A dia ialah 214 tolak 210. So jawapan dia apa? Okay, A dia mesti 4. So Z dia pula, Z dia ialah 84 tolak 82. So dapat dia 2. So yang ni X ialah 42. So X dia ialah apa? Helium 42. Okay, untuk yang bawah ni. So A ialah 210 tolak 210. 210 tolak 210. Lepas tu 8 untuk Z 81 tolak 82, yang ni kosong. 81 tolak 82 negatif 1. So dia ialah elektron, 0, negatif 1. Okay, satu helium, satu lagi. So yang atas ini merujuk kepada alpha decay. Yang bawah ialah beta decay. Right, last questions. Uranium continues producing a set of radioactive daughter nucleus until radium-228 is reached. Show the decay questions and find the total of alpha particles that are generated in this. This one. So, daripada uranium 23692, okay. So kita tak tahu dia akan jadi macam mana, tapi dia kata show the decay equation, find the total number of alpha particles that are generated. Jadi kita kena buat pelan-pelan lah. So daripada uranium ini, alpha particles ialah helium-42 helium-42, so dia akan dapat apa dulu? So kita tak tahu kita letak nama dia daughter lah, daughter D. So 236 dia akan jadi 232 sebab tolak 4. And 92 minus dia akan jadi 90. Alright, so untuk D plus dengan Y. Okay, so dekat sini kita akan dapat 1 helium 42. Okay, so yang ni pula D 23290. So it release another alpha. Jadi E lah pula. Okay, E ataupun okay, E, which is dia akan turun jadi 232 jadi 228. So 228 yang ni jadi 88. Yang ni lah radon. Okay, radon. Plus dengan helium 42. So how many alpha particles are there? We have 1 and we have 2. So the answer is 2 particles of alpha. Okay, 2 particles. Number of alpha particles are 2. Okay. So, is there any questions? Tak sempat nak tanya.